Good evening, everyone. My name is Andrew Fracknoy. I'm the Emeritus Chair of the Astronomy Department here at Foothill College, and it's a great pleasure for me to welcome everyone here in the Smithwick Theater and everyone hearing us on YouTube or on your favorite podcast channel to this sixth lecture in the 25th Annual Silicon Valley Astronomy Lecture Series. We've, for 25 years, brought astronomers and scientists from around the country and even the world to discuss the latest in their astronomical findings. These lectures are sponsored by three organizations that have a great investment in the public understanding of science: the Foothill College Science, Technology, Engineering, and Math Division, the SETI, the Search for Extraterrestrial Intelligence Institute, where our speaker works, and the Venerable Astronomical Society of the Pacific, which for more than 130 years has been doing what these lectures do, which is to bring astronomical information to the public in everyday language. We really appreciate their getting the word out, and we will continue to do the lectures next year, starting next October. So please tune in to information about the 26th Annual Lecture Series coming next school year. Now let me introduce our speaker tonight. Dr. Oliver White is a planetary scientist at the SETI Institute. His research focuses on unraveling the geological histories of the planets and moons with which we share our solar system. He's particularly interested in learning how their surfaces have evolved over the millions and billions of years. A member of the New Horizons mission team, he's particularly interested in the icy outer solar system worlds, and he has, this is wonderful, he has produced a geological map of Pluto to be published by the U.S. Geological Survey. Should we still call it the U.S. Geological Survey if they're making maps of Pluto? Shouldn't we call them something more cosmic? But anyway, these are the definitive maps of territories that you probably know if you're a hiker, and it's wonderful that Dr. White has made it possible for us to have an accurate map of the surface of Pluto. In fact, he is currently creating a similar map of Saturn's moon, Tethys. Let me now ask you to join me in welcoming, talking about science at the edge of the solar system, Dr. Oliver White.
Thank you very much, Andrew. And yes, the USGS does actually have an astrogeology division in Flagstaff, so they handle all matters extraterrestrial. Thank you very much, Andrew, and thank you all for coming. It's hard to believe that it's been almost 10 years now since New Horizons spacecraft flew past the Pluto system. I remember it very fondly, being part of the New Horizons team, and the great sense of discovery we all felt on that day, sort of just seeing this incredible world up close for the first time, and also 3.5 years later, as New Horizons traveled farther out into the solar system, seeing the much smaller object, Arrokoth, up close, the most distant object we've ever flown by in the solar system. So I'd like to share some of that sense of discovery with you today by taking you on a geological tour of Pluto and its moons, and also Arrokoth, to sort of show you what we found is sort of possible in this distant, very cold, and we previously thought inactive part of the solar system. So I'll first start off with sort of what we knew about Pluto before the New Horizons flyby. The short answer is not very much at all. Pluto was discovered back in 1930 by the American astronomer Clyde Tombaugh in Flagstaff. Back then there was a search for this supposed planet X orbiting beyond Neptune, so it was a sort of a campaign to try and find that. His search involved the painstaking method of taking photographs of the sky through a telescope several days apart and studying the plates to see if any of the dots had moved position in that time. And if you did find the dot had moved position, then it indicated it's an object in our own solar system as opposed to a background star. So he did indeed find such a dot in 1930 that was orbiting beyond Neptune, and so that was named Pluto and declared the 9th planet. And following that, further discoveries are pretty few and forthcoming, given how far away Pluto is. We know now it orbits the Sun once every 248 Earth years. It was found after not that long that it has an orbit very different to the other planets. It's very elliptical, very oval, not really circular like the other planets. So it sort of takes it very far, 7.5 billion kilometers at its farthest from the Sun and 4.5 billion kilometers at its closest. And it's also quite inclined to the orbits of the other planets as well, as you can see in the diagram at the bottom right. Over the course of the century, its mass was consistently revised downward, and it was realized that it's only by far the smallest of the planets. We know now it's about 2,400 kilometers across, about the fifth the Earth's diameter. But it was discovered in the 80s that it actually retains a thin atmosphere, quite a surprise for such a small body with such a low gravity. And it was discovered one very large moon in the 70s called Charon, that's about half the diameter of Pluto. And then in the 2000s, the Hubble Space Telescope discovered four more very small moons orbiting outside Charon. And as we now know, Pluto is merely the first object that was discovered in what we now call the Kuiper belt, which is this enormous disk of small icy objects that orbit beyond Neptune. We know of a few thousand, but we suspect there are probably hundreds of thousands. The next one after Pluto was only discovered in 1992. But that is kind of the main reason for why Pluto was downgraded as a planet, because it shares its place in the solar system with a lot of similar-sized objects. That's all I'm going to say about its sort of status being downgraded, but if there are any questions about it, I'm happy to answer them afterwards. So, in 1989, the Voyager 2 completed its flyby of Neptune, and that therefore completed the initial reconnaissance of the eight of the 9 classical planets in the solar system, and that left Pluto, which at that time was still the only known object beyond Neptune, as the only unexplored planet in the solar system, as sort of indicated by this 1991 USPS stamp. So there were various attempts to try and get a mission to Pluto launched, and eventually the New Horizons mission was the one that stuck. Here is the spacecraft being prepared at the Kennedy Space Center. It's about the size of a small grand piano, and it was launched on an express trip to Pluto with a quick flyby of Jupiter as well in 2006, the fastest launch in history, accelerating to 16.5 kilometers per second, but it still took 9.5 years to get to Pluto. And when it got there, this is what we saw after 85 years. This is the first time it was no longer the astronomer's planet, not just a fuzzy blob, even with Hubble imaging. So in July the 14th of 2015, it performed its closest approach. At that time, Pluto was almost 4.8 billion kilometers from Earth, or 31.9 astronomical units, where an AU is the distance between the Earth and the Sun. At that time, it takes 4.5 hours to transmit a signal back to Earth at light speed, and 9 hours if you want a return call. It's also extremely dim out there. This picture gives a sort of false impression of the brightness, but it's much dimmer than this. It only gets about 0.1% of the illumination we get on the Earth, and that means it's bone-crunchingly cold on Pluto, about 380 degrees Fahrenheit below zero. And so this was a flyby mission. New Horizons was zooming at a few tens of kilometers per second with respect to Pluto, so it just got one shot to fly by it, take as many images as it could, and then carry on out into the solar system. So what that means is the closest approach only lasted several hours, so we just had that short time interval to get as many happy snaps as we could before it carried on. So we only got to see one side of Pluto, called the Encounter Hemisphere, up close, which we saw saw it better than 1 kilometer per pixel. The rest of the Pluto that we saw was seen at varyingly worse resolutions. The worst of all was about 40 kilometers per pixel, seen several days out from closest approach. However, we also only saw the northern part of Pluto. So Pluto is kind of odd in that it and Charon, their axial tilt is very high compared to Earth's, 119 degrees compared to 23 degrees. So they kind of rotate on their side, kind of like the planet Uranus. So what that means is that they have extreme seasons. One hemisphere on Pluto experiences 124 years of constant sunlight, while the other hemisphere experiences 124 years of constant darkness. And so as New Horizons was flying by, the northern hemisphere was entering northern summer, so that was illuminated for all to see, but the sun latitudes are in constant darkness until probably another 100 years down the line when they'll start to get illuminated again. So we couldn't really see much at all in the southern part of it. So the coming slides, I'm going to focus on some of the weird and wonderful terrains that we saw across Pluto, how they surprised us, and what we think formed them, and how they fit into its geologic history. So the thing that really stuck out, even several days before we flew by Pluto, was this big, bright, heart-shaped feature on the surface that we call Tombaugh Regio, named after Clyde Tombaugh himself. And flying up close to this, we see that the left-hand side of this heart forms these enormous expanse of bright plains here. They cover about half the area of Alaska. This is what they look like in topography. They're both very low, and they're also extremely flat. They only sort of vary across sort of hundreds of kilometers by a few hundred meters or so. But also, very interestingly, we found that there's not a single impact crater seen anywhere on the plains. So impact craters form in the solar system when you have an object crashes into a planetary surface and it leaves a hole. The most famous example on Earth is probably Meteor Crater in Arizona. And judging by the number of impact craters you can see on the surface is kind of a proxy for how old the surface is. If you have a crater form and nothing else happens to it, then it will just stay there. But if you have some geologic process that wipes it out, like sort of covered by volcanic flows or eroded by fluvial action, then it fills in and is eliminated, and sort of its indication of that the surface has been resurfaced. So Earth has very few impact craters because we have a very active geology that wipes them all out. The moon has a lot because there's been no process on the moon to wipe out all the craters that formed on it when soon after the moon formed billions of years ago. So on Pluto, we see these yellow dots. There are a lot of impact craters outside of Sputnik Planitia, but none on Sputnik Planitia itself. So some process, it's not as though all the craters are just happening to miss Sputnik Planitia. They are forming there. It's just that some process is occurring to wipe them out. And so the mystery sort of another piece of evidence we see as to what's going on here is that Sputnik Planitia's composition is dominated by this bright nitrogen ice. So this is the first of a handful of very exotic ices that we encounter in the distant solar system. The surface temperature and pressure conditions at atmospheric pressure and temperature conditions at Pluto are such that nitrogen can exist as an ice, not just as a gas as we experience on Earth. And a lot of it seems to be concentrating here in Sputnik Planitia. But it's an ice that's rather not very similar to water ice at these conditions, because it's actually quite runny, it's quite viscous. Probably the material that's best to compare it to is a tar pitch. This is the Queensland pitch drop experiment in Australia, where they stuck this bunch of pitch in a funnel back in 1927, and since then 9 drops have fallen into the beaker below. So this gives you an idea of how it behaves over on a short time scale. It behaves brittle. If you smash it with a hammer, it will break apart. But on a sort of long geologic time scales, it flows very slowly. So that's kind of gives you an idea of how nitrogen ice behaves. So we know that this terrain is very flat, it's got no impact craters, and it's made out of all this runny nitrogen ice. So let's have a closer look at Sputnik Planitia and see if it sort of, if we can sort of get an idea of sort of why it appears the way it does. And if we look at the central and northern part of Sputnik Planitia, it's actually these plains are divided into this cellular pattern here. So you can see these cells, each divided by this sort of ridge trough sort of system sort of between them. There are about 200 of these. They're on average 32 kilometers across, typically on average about a third the size of Santa Clara County. And so we looked at this and we thought, well, given what we know about nitrogen ice, these seem to be what are convection cells. So basically, we think that the nitrogen ice is actually being mobilized by the very low heat flow, just a few milliwatts per meter squared, that it's trickling out of Pluto's interior. Probably just the whatever radioactive elements are in its core is still sort of trickling out a little bit of heat 4.5 billion years after it formed. But this is apparently enough to cause this nitrogen ice, which again is slightly runny, to actually, parts where it's heated up, it's rising towards these cell centers where it bulges up the surface, and then it sort of travels laterally as it cools, and then sort of pinches at this trough ridge intersection between the cells, and then before it descends back down to the bottom of Sputnik Planitia. And the reason we think that it all concentrates in this one spot is because it's actually filling a giant impact basin that formed early on in Pluto's history. It all basically sort of just infilled this sort of what is kind of a giant cold trap there at the bottom of this impact basin. So yes, it's essentially, if you will, a giant nitrogen ice sea that is dominating this part of Pluto that we flew past. And we've calculated that based on what we know about the properties of nitrogen ice, that the surface can probably renew itself in just about 500,000 years, which is a drop in the ocean in geologic timescales, and is certainly enough to short enough such that any crater is not going to last very long before it's eliminated by this sort of active process taking place there. However, that's not quite the end of the story with Sputnik Planitia, because if we look down south, we see the cellular planes don't seem to occur here anymore. We think that the nitrogen ice is rather thinner here, probably less than 1 kilometer thick, which is not thick enough to actually support active convection. What we do see instead are these enormous swarms of these closely spaced off and elongate pits. And so nitrogen ice, as well as being easily mobilized and causing to flow by sort of interior heat, it also is quite unstable a bit at the surface, and it can actively sublimate into Pluto's atmosphere. So sublimation is when you have a solid going to a gas and jumping out the liquid phase. We're most familiar on Earth with sublimation of dry ice, like in old school horror movies. You see it used there for atmospheric effects. But we think the same thing is happening here on Pluto and forming these large pits in the ice here as it sublimates into Pluto's nitrogen atmosphere. And the reason why we think that it sort of creates these odd sort of wave-like thumbprint sort of patterns is because the ice, while it's not actually convecting, it is probably still glacially flowing across the surface here, and probably the sort of the stress that imparts on the pits is actually causing them to stretch out. So they're kind of revealing stress fields of sort of indicating the flow of the ice here. So now we move to another extraordinary aspect of Sputnik Planitia, which are the giant mountain ranges that line its western edge. So this is one of my favorite photos that we got of Pluto, sort of soon after closest approach, looking across its surface at a low angle. You can see Sputnik Planitia on the right, where all these dark dots, each of those is a pit. And you can see these one of these enormous mountain ranges here called Tenzing Montes, with these dramatic shadows cast across the surface. And you can also see some more mountains popping up on the horizon, and it's the haze layers in the atmosphere above that, so extremely dramatic image. But these mountains They're pretty large, some of them. They can rise up to 5 kilometers above the plains. That's pretty much the same as Kilimanjaro, the tallest mountain in Africa, rising above its base. And they can be very steep, up to 30 degrees. So they can't be made out of nitrogen ice, these mountains. They have to be made out of something more rigid that can support these slopes. And from this compositional map we got by sort of like, as with the nitrogen, sort of analyzing the light reflected off Pluto's surface to get an idea of the composition of its surface. We find that the mountains, as with the, sort of much of the rest of Pluto, is made out of water ice, which is really, along with Pluto and most of the, and pretty much all the outer solar system moons, this is what is sort of the bedrock and forms their crust, unlike silicate rock in the interior terrestrial planet. So out at Pluto conditions, water ice is much stronger than it is on Earth. It's kind of like granite, so it could easily support the steep slopes that we see sort of these mountains. So how do these mountains form? So if we look up close, these mountains, the first thing we noticed about them is that there's really no sort of orderly arrangement to them. They're just these sort of jumbled blocks, sort of thrust chaotically together clustered in these ranges. A couple of them actually sort of seem to have escaped the pack and sort of stuck out in towards the center of Sputnik Planitia. And there are also a few instances where we see what look like little ponds of nitrogen ice that separate the mountains themselves. So one thing we noticed about this part, this edge of Sputnik Planitia, is that it's quite heavily fractured or tectonized, as we say. There are lots of fractures that intersect the edge of Sputnik Planitia here. So what we think is that this is a western edge of Sputnik is a sort of a special part where this fracturing has weakened the crust here, and the crust has been intruded, probably by glaciation of Sputnik Planitia that has acted to basically dislodge these tectonized, fractured blocks from the crust and cause them to basically just sort of be grounded at the edge of Sputnik Planitia, surrounded by nitrogen ice, and just sort of forming these enormous, what you might call a giant log jam of enormous fragments of crust now just stuck sort of at the edge of Sputnik Planitia. And one thing to consider about the relative densities of nitrogen ice and water ice is that water ice is slightly less dense than nitrogen ice. The density contrast is about the same as liquid water and water ice on Earth. So if you take a block of water ice and dunk it in a nitrogen ice sea, much of it, a little bit of it will poke up sort of above the surface, but much of it will be below. So a lot of these blocks at the edge of Sputnik are legitimately grounded in Sputnik, but some of these smaller blocks out towards the center of Sputnik, these ones may be far enough to the center where the Sputnik nitrogen ice is deeper, such that they're probably actually floating within the denser nitrogen ice as like water icebergs in a nitrogen ice sea and getting pushed around by the convection currents there. So yeah, some more pretty weird stuff that we never anticipated prior to New Horizons. And then we now move sort of to the eastern half, or the eastern ventricle of the bright heart on Pluto, East Tombau Regio. This area is bright like the west, but it's a very different kind of terrain. It's sort of uplands now, and you can see the sort of very jagged, kind of pitted terrain here with sort of these smooth plains sort of separating the sort of more elevated portions. We think this is all sort of nitrogen ice, like Sputnik Planitia, but we think that it's actually sort of redeposited from nitrogen ice that is sublimated from Sputnik and just redeposited on this eastern terrain here. And so we think that's what's sort of coating the landscape here. And nitrogen ice, again, it's kind of runny, and so it will sort of flow downhill. So it's basically covering the floors of these basins, separating the elevated terrain here. And we see very peculiar features here that are rather similar to features that we're familiar with on Earth, which is what appear to be nitrogen ice glaciers flowing from these uplands and reconnecting back into Sputnik Planitia. So we see what looks like, here, I think I can do it there. So we see what looks like these valleys that connect sort of basins in East Tombau with Sputnik Planitia. We see these dark bands here. These look sort of lateral bands following the line of the valleys here, and these look very similar to moraine trails and glaciers on Earth, like this example in Greenland. You can see where these rocks have like fallen onto the glacier sides and been carried along with glacial flow to the flow out into the Atlantic Ocean in this case. We think the same thing is happening with glacial flow on Pluto. It's just water ice blocks falling onto a nitrogen glacier and being carried out into Sputnik Planitia, and you can sort of see the sort of these flow terminations where the glacier seems to sort of peter out up here. So I kind of liken it to like a cosmic game of rock, paper, scissors, where you get similar landforms forming in different parts of the solar system, but with very different materials, depending on the environmental conditions. So on Earth, you get water ice glaciers cutting through rock. On Pluto, you get nitrogen ice glaciers cutting through water ice. So the roles are rather different depending on the environmental conditions and what solids are stable, what materials are stable at the surfaces of these worlds. And now if we carry on farther east, we get to what I think is one of the most alien-looking terrains, most sinister terrains seen on Pluto, particularly because we flew by it when the lighting was quite low and it cast these eerie shadows. It's what we call this bladed terrain. So this terrain, you can see it it forms these separate sort of large-scale swells, sort of like several tens of kilometers across and several kilometers high, separated by these fault lines here. But the upper surfaces of these swells show this kind of rippled, we sort of thought of as almost snakeskin texture of these narrow aligned ridges. You can see them here as well in this sort of north-south oriented image here. They tend to be like a few hundred meters tall and separated by a few kilometers. So this is kind of perplexing, but we saw that this all of the bladed terrain appears to be made out of methane ice. So along with nitrogen, methane is another of the materials that is gaseous on Earth, but is stable as a solid on Pluto. And so we think that this is basically a giant repository of methane ice on Pluto. We think that in sort of Pluto's middle age, there was a great sort of deposition event of atmospheric methane that sort of deposited across Pluto's equatorial regions to form these deposits. But at some point in later on in Pluto's history, there was some sort of climate change that preferred sublimation of methane ice over deposition, and that caused basically the methane ice to sublimate away and sort of create this sort of jagged, sort of a rippled texture, which is essentially a sublimation texture, sort of a bit like the pits in Sputnik Planitia. We think it sort of bears some resemblance to some sublimation features we see in water ice on Earth at sort of high elevation, low latitude snowpacks. For example, these sun cups you can see in the Yosemite National Park, and also penitentes, these much more jagged formations in Chile you can see on the right. We think a similar thing is happening with the bladed terrain on Pluto, but as with the sort of nitrogen ice glaciers, it's happening at a much different scale with a different material, methane in place of water ice. So yeah, it's another peculiar way in which we can see sort of in the farthest, least expected corner of the solar system, these similar landforms to on Earth, but with very different materials at play. And then if we go south of Sputnik Planitia, we encounter a unique mountain on Pluto that has kept all our heads scratching even almost 10 years after we flew by Pluto. This is Right Mons, this mountain that's about 150 kilometers across and 3 to 4 kilometers high, but what makes it special is that it has this enormous central depression, 70 kilometers across and up to 5 kilometers deep, so actually deeper than the mountain is high. So us being a bunch of simple planetary scientists, we see a big mountain with a hole in the middle, and naturally we think volcano, and honestly, we kind of still thinking that 10 years after. We haven't really come up with a better hypothesis. We think that possibly it might be some sort of volcanic vent, the central depression. But the thing is that it's enormous compared to the vents that we see on similar-sized shield volcanoes in the inner solar system. You can see it in this graph at the bottom left. There's Mauna Loa on the big island of Hawaii with a very small sort of summit caldera compared to the size of the volcano itself. Right Mons, shown at the same scale for comparison, is you can see just how large the central depression is compared to the mountain itself. You could pretty much turn Mauna Loa upside down and it would fit nicely into Right Mons' central depression. So that's, yes, exactly why it would have such a big central depression, we're not sure. And also, this is an example of what we call a cryovolcanic edifice. Cryovolcanic basically implies that it's actually erupting some sort of water ice-based slurry instead of rocky lava. And cryovolcanism, it's a field that's kind of in its infancy. There aren't that many locations in the solar system where we think it's happened, and it's kind of somewhat difficult to recognize what landforms are indicative of it, since it probably progresses in a way that's sort of quite different to the familiar sort of rocky lavas that we see on Earth. So whether it is sort of volcanic, we're still not entirely sure, but whatever it is, it's certainly pretty young. There are very few craters, so it's maybe less than 1 billion years old. So if it is volcanic, then it indicates that such volcanism was possible on Pluto even quite late on in its history. So all the terrains I've shown you so far are all linked by the fact that they either have no craters or just very few craters. So they're all pretty young. They date, probably the oldest is probably dates to like Pluto's sort of late middle age. But when we get to the Arctic terrains, we sort of have a quantum leap in terms of the number of craters we see. There are certainly dozens sort of spread across the landscapes here. So that means that these terrains are quite a bit older, probably in certainly the first half of Pluto's history is when these were last resurfaced. They show some interesting features, particularly Voyager Terra, north of Sputnik Planitia, has a bunch of these sort of broad valleys that are kind of not much elevated, not much above Sputnik Planitia itself, and some of them take on this quite provocative, sinuous sort of qualities that you can see, like this one at the bottom left here. And we think that these valleys may actually have hosted ancient nitronized glaciation, like we see in East Tombaugh Regio today, but with the glaciation no longer being stable in these parts of Pluto, in this part of Pluto. So yes, so this evidently hasn't hosted such glaciation for billions of years. On the right is Pioneer Terra to the northeast of Sputnik. This is kind of interesting because it shows this kind of softened, the terrain here sort of shows this softened, rounded appearance, kind of protuberances, topographic protuberances tend to be quite rounded, and sort of valleys tend to sort of reach kind of pinch to a sort of V shape. This sort of texture, which is certainly quite apparent when you compare it to sort of the more jagged branching valley networks located next to them, which probably was also caused by ancient glacial flow. But this rounded texture is what we call an accretion texture. I guess it's probably familiar on Earth if you let your freezer sort of like get too cold and builds up a freezer frost. It kind of builds up this sort of puffy, pillow-like texture there. And we think the same thing has happened on Pluto here with accretion of methane ice here. This area is quite rich in methane. And we think that's sort of probably sort of more than 3 billion years ago, this area experienced a methane deposition episode that just coated this terrain to create this accretional texture, but which sort of ceased probably as the bladed terrain deposits sort of started to form and build up much thicker deposits in the equatorial regions. And then we travel to the last place on Pluto I'll focus on, which is Belton Regio to the west of Sputnik. So this is by far the oldest terrain we see on Pluto. This is where we see the most impact craters. Belton Regio is this very dark region extending west from Sputnik Planitia, larger than Alaska. And you can see it's characterized by this very dark deposit that blankets all the terrain here. So This material we think is actually this stuff called tholins. Tholins are these complex molecules. They're often sort of thought of as hydrocarbons, but they actually contain other stuff as well. But they're formed by when you irradiate methane in Pluto's atmosphere. It forms these complex molecules that then settle out onto the surface, and they build up over time. So this should be happening everywhere on Pluto, but the fact that we only see them building up in thick deposits here suggests that nothing has acted to sort of wipe away these tholins. So along with the fact that this area is very cratered means that this is another indication that this is some of the oldest surface we see on Pluto. And we see it actually as a microscope picture there of some tholins that were generated in a lab at NASA Ames. And yeah, they start off orangey, but as you expose them to more and more ultraviolet light, they actually turn to a dark red color. And like I mentioned before, this is some of the most fractured, tectonized part of Pluto that we see. It features these sort of very large fracture systems extending across its surface. Some of them can reach a few kilometers deep. In the case of Virgil Fossa here, 3 kilometers, 3-kilometer high fault scarp here, about twice as high as the Grand Canyon, is deep. All the tectonism, all the fracturing we see on Pluto is extensional, just where the crust appears to be breaking apart. There aren't any compressional features anywhere. And we think that this is consistent with the fact that Pluto, having a subsurface water ocean that was thick early on in its history, but over time it's gradually cooled and frozen, and when water freezes, it expands and basically causes Pluto to burst its skin. And we think this is the manifestation of that on the surface, these extensional fracture systems sort of cutting across its surface here. So yeah. And then just finishing up on Pluto, a quick slide just on its atmosphere. Pluto does have a very thin nitrogen atmosphere, but it does have smaller components as well, including methane and other hydrocarbons, acetylene, ethylene, and ethane. And it's these more complex molecules that accumulate into little particles and scatter the sunlight to produce these haze layers. It's not the only place in the solar system we see that. We also see similar haze layers on Titan, Saturn's giant atmosphere-covered moon, and this is one of the coolest photos to come out of the flyby. This is an actually true color view of Pluto's haze layers. It has the same scattering as effect as we see on Earth. That's why sort of the Earth's sky is blue, and Pluto's as well. But it has an extremely thin atmosphere, only 100,000 times less than Earth's. But we think it probably differs quite a lot across an orbital cycle based on how much of Pluto's sort of volatile ice deposits are being illuminated by the sun. If you have sometimes in the orbit when you have sort of much more sublimation happening, that can probably cause the surface pressure, atmospheric pressure, to increase by maybe orders of magnitude. So now we move on to Charon, Pluto's largest moon. So it's actually the largest moon with respect to its parent body in the solar system, being a diameter half that of Pluto's. You can actually compare the real estate we're dealing with on Pluto and Charon here. If you were to unfurl all of Pluto's surface area, it would cover most of North America, while Charon's would cover about half of the lower 48. And in fact, yeah, the Pluto-Charon system is actually the most similar in the solar system to the Earth-Moon system with respect to the size of the moon to its parent body. But given that Pluto's and Charon's are so similar to each other, they're actually been coined, the system's been often coined a binary planetary system. They're actually so similar in size that the center of mass of the system, called the barycenter, is actually outside of Pluto, so they orbit around each other, with Pluto describing a small circle around the barycenter and Charon describing a larger circle, sort of like an Olympic hammer thrower describing a small circle and the hammer a larger one. And I was going to mention, they're also tidally locked to each other, the same way that Earth's moon is tidally locked. It always presents the same face, so its orbital period is the same as its rotation period, so it's the same for both Pluto and Charon. Their orbital period, they always present the same face to each other as they rotate around each other every 6.5 Earth days. So looking at Charon's geology, the first thing we noticed is that a lot of it is very cratered. So we think that Charon's surface is mostly extremely old, more than 4 billion years. So not much has happened on its surface since soon after it formed. I mean, for one thing, it doesn't have an atmosphere, so it doesn't have these crazy volatile ices like nitrogen and methane that are really the main source for all of Pluto's geological activity today. But we can see that from what's recorded on its surface that it did have an active geology in its early history. Like Pluto, it also does have enormous canyon systems extending across its surface, in fact, even bigger than what we see on those on Pluto. Its in-counter hemisphere is dominated by these canyon systems stretching some southwest to northeast, and some of them form what we call graben. These are where you have two sort of steeply dipping normal faults that basically where the crust is pulling apart, and you get this sort of the block in the middle sort of subsides down. Sort of the most obvious example of that is this Serenity Chasma, about more than 50 kilometers across and 5 kilometers deep, with some very steep walls where these landslides forming on them. And there's another good example, Arrokoth, which we saw on the limb of Charon over on the right. So we think they're formed by the same process that formed the ones on Pluto. We think Charon also had a sort of water ocean early in its history that subsequently froze and caused it to burst its skin, forming these enormous canyon systems. This topography map on the top right shows that there's kind of a dichotomy on Charon's surface between this sort of undulating, blocky configuration in its northern terrain and what seemed to be much flatter terrain that we call Vulcan Planitia in its equatorial regions. This is a close-up of these equatorial plains. One peculiar thing we noticed about them is that they feature what we call these moated mountains. They're these mountains sticking above the plains that sort of reach sort of 3 or 4 kilometers above them, but which are surrounded by these moats a few kilometers deep. Clark Mons and Kubrick Mons are the best examples that we've seen so far. We also noticed that surrounding these plains are sort of this trough separating them from, sort of shown in these sort of dark, indicating low elevation here, this trough separating them from the blocky uplands. So given how flat this terrain is, we've hypothesized that what these plains are is possibly a cryovolcanic sort of lava flow that was released from Charon's interior early in its history, perhaps released through the same cracks that I mentioned in the previous slide, and spread out across the surface. And such a flow would have been quite thick and viscous, so it's possible that if it once encountered pre-existing topography, it may have, like the edges of sort of the depression in which these plains are located, or indeed these pre-existing mountains, it may have stopped short and sort of left this moat kind of sitting there passively, sort of while it just froze solid. So in that sense, it might be possible to sort of look at these plains as being kind of like an icy analog to the lunar maria, the seas on our moon, which are formed by giant outpourings of basalt filling depressions on the moon, sort of between mostly 3 and 4 billion years ago. Maybe a similar thing happened, but with sort of water ice-based lavas spreading out across Charon's surface in its early history. And then probably the most one of the weirdest features we saw on Pluto is the fact that it has a dark north polar cap, which is at the moment informally called Mordor Macula. In case you haven't realized already, the naming theme on Charon is mostly sort of sci-fi and fantasy. But it's very odd to see a dark polar cap in the solar system. Usually they're brighter than the rest of the body. This feature is pretty much sort of directly it's oriented directly over the North Pole, and you can see at the bottom right, it's quite dark red, sort of like Belton Regio that I showed you on Pluto earlier. So we think that it's due to the presence of tholins, but the trouble with that is that we haven't seen any methane on Charon. There seems to be no obvious source for this methane to be converted into tholins. But we realized that the source of Charon's tholins might actually be Pluto itself. So during the flyby, we measured that Pluto's atmosphere is actually gradually escaping from it. Pluto's low gravity combined with pressure from solar wind actually causes some of its atmosphere to be stripped off and carried farther out into space. And there are particular times during Pluto and Charon's orbits around the sun that Charon is kind of aligned behind Pluto, directly downwind, so it would actually catch, in rare instances, some of this atmospheric gas being stripped off Pluto. So we think that it actually catches some of this methane that is sort of trapped, basically trapped within the polar regions during the extremely cold winters, which, like on Pluto, the winters last for like 124 straight years of darkness. And then when it gets around to summer, some of this methane sublimates away, but some of it also remains trapped in the ice and basically just stays there to be processed into these tholins by the sunlight. And that can only really happen at the pole. And since we didn't see Charon's south pole, we're not really sure if it's also dark, but this sort of hypothesis does suggest that its south pole is also dark, like its north one. And then just a quick slide on the Pluto's small moons. So at the top here is a diagram showing the Pluto system to scale, with Pluto, the barycenter, and Charon. And you can see these tiny little moons. They barely register as dots on this slide, but they're indicated by arrows. But they orbit much farther outside of Charon. And you can see them into scale with Charon here. They're only, the largest, Nix and Hydra, are only sort of about 40 kilometers across. Styx and Kerberos are rather smaller. And you can see they're kind of a bit like asteroid-like. They're kind of potato-shaped, kind of elongated, and they're pretty bright, so they're probably mostly made of water ice, like Pluto and Charon themselves. And they only have Nix and Hydra. Are the only ones we can resolve craters on, and they only have a handful of them, but that's still enough for us to reckon, given that we're not dealing with very large areas here, that they're probably more than 4 billion years old. And we think they actually might be detritus from a giant impact that we think originally sort of impacted Pluto to create Charon. We actually think that Charon was created the way that Earth's moon was created, by a giant impact early in its history that caused enormous sort of disk of material to form around the parent body and eventually coalesce into a moon. We think that these may be relics from that were ejected into the outer Plutonian system. So, okay, I might just have a quick breather before we carry on into the outer solar system. So, yeah, that wasn't the end of the adventure. It was always the plan that New Horizons, after it had flown by Pluto, would carry on farther out into the Kuiper belt and study another little object. The trouble was, when it launched in 2006, such an object had not yet been discovered. It was only in 2014 when the Hubble Space Telescope did a survey of the part of the Kuiper belt that New Horizons would fly through, that we discovered a handful of candidate objects that it could fly past, and eventually we settled on this one particular one, Arrokoth, which would be sort of best one to fly by, which with the available fuel reserves. So just a quick primer on the Kuiper belt itself. It's much larger than the perhaps more familiar asteroid belt. It extends from Neptune to about 55 astronomical units, 20 times as wide as the asteroid belt, but it's also pretty sparsely inhabited. We think probably in between 1/25 to 1/10 the mass of the Earth. We think there might be more than 100,000 decent-sized objects out there, and like Pluto and Charon themselves, they're mostly pretty icy. I just quite like this little sequence of images here showing the discovery of Arrokoth, and also sort of showing the power of Hubble Space Telescope. It's sort of kind of like Clyde Tombaugh did almost a century ago. They're basically, these show sort of separate images taken at different times that show Arrokoth against the background of these much brighter stars. It's a great testament to Hubble's power that managed to image this sort of above the noise levels and these just much brighter stars surrounding it there. So this slide, before I carry on to Arrokoth itself, I just want to impress on you exactly how much Pluto and Arrokoth differ, because even before we flew by Arrokoth, we knew from studying its orbit that it was going to be a very different beast to what Pluto is, not least because, I don't know if I mentioned in the previous slide, it's also much, much smaller, only about the size of like the larger of the two small moons of Pluto. So don't worry, this graph isn't that scary. It's basically just showing each one of these dots is a discovered Kuiper belt object, and the bottom axis is showing their distance from the sun in AU, and the y-axis is showing the eccentricity of their orbit, so again, how elliptical they are, how much they stray from circular, and the color of the object, whether it's blue or black, indicates the inclination of the orbit, and at the bottom left we have Neptune here, which forms the inner edge of the Kuiper belt and which has a pretty much circular orbit, so it's basically 0 on the y-axis, and we have Pluto and Arrokoth indicated with arrows here. So Pluto is what we call a resonant Kuiper belt object. There are two kinds of resonant objects. There are the Plutinos, which Pluto giving its name to that, and these orbit in what's called a mean motion resonance with Neptune. In the case of the Plutinos, it's a 3-2 resonance, so for every 3 orbits that Neptune makes to the Sun, the Plutinos make 2 orbits. And then farther out, in what is a less stable resonance, you have the jokingly named Tutinos, so for every 2 orbits that Neptune makes to the Sun, these make 1 orbit around the Sun. So you can see that there are a lot of these resonant objects. They sort of cluster at these particular distances, about 39 and 48 astronomical units from the Sun. And these typically show pretty high orbit eccentricities. You can see they plot quite high on the y-axis. And most of them are blue, which indicates they have quite high inclinations. So compare that with Arrokoth down at the bottom here. Arrokoth is one of what we call the classical Kuiper belt objects, which mostly orbit in between the resonance. These do not show any mean motion resonance with Neptune. These are divided into two classes, the hot and cold classicals. It's not actually referring to temperature, somewhat confusingly, but rather orbital dynamics. So the cold classicals are in very circular, low inclination orbits. The hot ones have much sort of more elliptical orbits and higher inclinations. You might be able to see that in this little diagram of them. The cold ones are all kind of in this flat plane orbiting alongside the other planets, while the hot ones, in green, they go sort of quite above and below the plane of the other planets, and they're also the ones describing these sort of wacky, sort of elliptical sort of orbits in this plan view, while the red ones, the cold ones, are all sort of in quite straightened circular orbits. So the reason we think that the reason we think that we have these different resonant and classical Kuiper belt objects is because the resonant ones, and perhaps also the hot classical ones, did not originally form in this outer part of the solar system. We think that they formed in the inner solar system, and that they were actually sort of based on the gravitational influences of the giant planets. They were actually forced out into this sort of distant part of the solar system. In the case of these, the Plutinos and the Tutinos, we think that since they're so closely tied to Neptune's orbit, that they are actually shoved out by Neptune and forced into these resonant orbits. Meanwhile, the cold classicals, like Arrokoth, we think they actually formed in place at the beginning of the solar system in this distant part of the solar system and haven't really moved from there since then. So basically, even before we saw Arrokoth, we knew a couple of things: that it probably had not really shifted from its place in the solar system, unlike Pluto, which had kind of been shepherded there, but also the fact it's much smaller probably indicates that it's also much more primitive compared to the much larger Pluto, which we've seen can support all this crazy geology. And that was kind of borne out by the observations that we saw 3.5 years after we flew by Pluto. We flew by Arrokoth. You can see the flyby sequence here as it got closer and closer. These are some of the flyby stats, which I won't go over them, but they're basically all just more extreme than the Pluto, much farther out and dimmer and much colder. But the first thing you'll notice about Arrokoth is that it's not actually one single object. It's what we call a contact binary, two separate objects that are joined together in this kind of a neck region here, with the small lobe being called Wiyu and the larger lobe being called Weinu there. So just a sort of discussion of some of the geology of Arrokoth. One thing to note is that it sort of looks like they're kind of spherical in the image on the left, but actually some of the imaging that we got sort of flying past it, we realized that they're actually quite flattened, so it's almost like a flat snowman. And they're really, for an object of these size, like each is sort of more than 10 kilometers across, they're really some of the flattest objects that we've yet seen in the solar system. They rotate once about every 16 hours. And kind of like Pluto, they're also very highly, their axial tilt is very high. So yeah, they orbit sort of, they rotate kind of edge on to the sun. One thing we noticed sort of about the large lobe in particular is that it has these, where is it? Okay, can't find the mouse, but anyway. But it's sort of indicated by asterisks anyway. It sort of seems to be divided up into sort of this lumpy configuration, sort of these sort of rounded lumps with these boundaries between them that are sort of easier to see. Oh, there it is. Easier to see where the sort of the shading is quite at a low angle here. We think that this might actually be an incredibly primitive texture here, where these are each of these lumps are actually smaller planetesimals that coalesced at very low impact velocities, probably only several meters per second, to basically form the larger lobe, and have not really been modified since then. It's just a texture that hasn't really changed since Arrokoth originally formed. On the smaller lobe, we see a large depression that we've called sky crater, and we do think it's an impact crater. There isn't really a similar sort of lumpy, as obvious a lumpy texture there, and we think that maybe the impact of sky acted to obliterate sort of any of the obvious sort of lumpy texture that we see on the larger lobe. We do see, particularly again here where the shading is quite low, we do see a bunch of pits on Arrokoth. These might be impact craters, but they might potentially be sublimation pits or possibly even collapse pits. There's a boundary between two of these sort of accretional units here where we see a little, what looks like a chain of pits. So it might be sort of surface collapse into sort of voids inside the large lobe here. If these sort of accretional units came together at low velocity, it's possible there might be a lot of sort of empty space, sort of pore space inside the large lobe. We also see there's some brightness variation across the surface. We see these bright patches, sort of what we think are sort of depressions, where sort of there and areas of high slope. It's most obvious at the neck between the two lobes, which we think has some of the highest slopes on Arrokoth, because you can imagine it has kind of a wacky gravity field, given that it's sort of two objects joined to each other. You have quite high slopes and gravity where they're connected. So this might be some sort of fine-grained material that has sort of gradually moved down slope and collected to form these bright deposits in sort of deep areas. And kind of like I've shown you on Charon and Pluto before, it does have a very darkened red surface comparable to a kind of Belton Regio on Pluto. So we think, again, this is probably due to irradiation by ultraviolet light of hydrocarbons on the surface. In fact, the main thing, we haven't really seen any water ice. The main thing we've seen on the surface is methanol. But yes, it's, again, another indicator of its great age. And again, this is probably giving a sort of a false impression of what you'd actually see on Arrokoth if you were with the naked eye. It's actually much darker. It's kind of like more like potting soil. So given how far away we are in the solar system, and given that it's very dark, it's pretty difficult to make out with the naked eye. We had to use long exposure when photographing it from New Horizons. So this is kind of a little sequence of how we think it's formed at the top. There's been a lot of modeling of how sort of contact binaries should form. This shows an example of sort of a collapsing dust cloud that sort of forms initially these larger objects and then sort of coalesce to form just two. And this is sort of an illustration of that artistically below. So yeah, we think that there was this rotating cloud of small bodies sort of for about 4.5 billion years ago that gradually coalesced to form these, sort of probably maybe even form a disk of material, and gradually these two larger objects sort of gobbled up everything else, and maybe some more smaller objects were thrown out of the system. The fact that Arrokoth is quite flat may be a relic of the fact that it formed from a sort of a flattened disk. So the fact that these accretional units kind of all just piled on top of each other, sort of in this sort of flattened configuration. And so initially they orbited each other, the two objects, and got closer and closer until they eventually touched and basically gave you the Arrokoth we see today, which we would argue is the most primitive object we've yet seen up close in the solar system. Hasn't really changed much at all in the 4.5 billion years since it formed. And that makes Arrokoth kind of an interesting feature to compare with comets that we see coming into the inner solar system. So we can actually, a lot of Kuiper belt objects are actually able to determine their shapes by seeing how they occult light from stars when they pass in front of them. You can actually get a better idea of what their shapes are than if just directly imaging with Hubble or any other telescope. And so we've managed to determine that they're actually quite common in contact binaries like Arrokoth and cold classical Kuiper belt objects, more than 30%. And out of the handful of comets we've seen, we've only seen about 6 close up, but we found that about 70% of those are also contact binaries. And comets, at least short period comets, we think are probably originated in the outer solar system but were perturbed onto these much more elliptical orbits that take them very close into the solar system. Some examples being Halley's Comet and Comet 67P, both of which have been seen up close by spacecraft. So we think that probably Arrokoth is kind of formed of the same kind of stuff that comets are formed by. The difference is that comets, since they've been perturbed and gone into the inner solar system and travel very close to the sun, they display much more modified surfaces. They've been subjected to all this much higher heat from traveling so close to the sun, and they've experienced a lot of sublimation that has caused a lot of their ice to be blasted off and create these much more jagged, evolved morphologies. Arrokoth, on the other hand, is just being a cold classical Kuiper belt object, has just formed in this very distant part of the solar system and has not moved from there since then. It's just stayed in this stable circular orbit. So it's maybe, if you like, a comet that never really got to be a comet, and it's preserved its rounded sort of accretional texture pretty much intact over the last 4.5 billion years. So the last few slides now, this is just where New Horizons carrying on into the outer solar system. It's expected to last into the mid-late 2030s. It's power source. It's currently about 62 astronomical units from the sun, so it's almost twice as far from the sun as when it flew by Pluto almost 10 years ago. And it's hot on the heels of 4 previous spacecraft that are also exiting the solar system, the 2 Pioneers, 10 and 11, and both Voyagers. And so there was an idea to sort of search for another flyby target, but Earthbound telescopes haven't found anything that it could fly by, so it's not really going to see anything else up close, and so it's going to sort of spend the rest of its days doing heliosphere measurements, measuring the change in the solar wind as it exits the solar system, but it also makes astronomical observations and also observations of distant Kuiper belt objects as well. And this slide just sort of gives a cool impression of just how far it's traveled. New Horizons has traveled far enough such that actually the sort of position of stars in the sky is starting to look different to how they look on Earth. So it actually conducted this experiment about 5 years ago, whereby New Horizons was trained on a couple of stars that are quite close to Earth, Proxima Centauri and Wolf 359, and at the same time photos were taken on Earth, and you can sort of see the parallax effect here as New Horizons have traveled sort of many tens of astronomical units away from Earth. The positions of these stars are sort of shifted slightly with respect to the background of much farther stars that are much farther away. And you can see the effect is heightened for Proxima Centauri because it's closer at 4.2 light years than Wolf, which is slightly farther. So it's a pretty neat effect. And this, if we ever become a true spacefaring species, this is pretty much how we would guide ourselves around the universe, is looking to see how positions of stars change with respect to each other. So yeah, here's the last slide, but this I think just conveys nicely sort of just the sense of discovery that we had almost 10 years ago. Pluto, up until then, was sort of regarded as the astronomer's planet. It was really just a point in the sky. Even Hubble Space Telescope couldn't really sort of resolve anything, but in the space of just a handful of days, it came sort of, we saw these fully fledged worlds with these landforms that we never expected to see. It just surprised us so much. And what sort of geologic activity is possible in this cold, frigid part of the solar system where we didn't expect sort of anything really of that much of interest to be there, but we had to go there to find out, and it pleasantly surprised all of us, and it pretty much makes us wonder what other sort of hidden secrets are hiding out there waiting for us to discover. So thank you very much, and happy to take any questions.
Let me ask as the first question, if I may, what most surprised you in all this discovery? Was there something that was the most unexpected for you?
I think it's really just the incredible diversity that we saw on Pluto. Because, I mean, when the great reveal happened on the morning of July the 14th in 2015, we really didn't know where to look first. There were, I mean, like we haven't even seen the best images by then, but immediately our sort of eyes were drawn everywhere all at once. I mean, from what we'd seen thus far in the outer solar system, we thought there might be we were probably expecting a lot of craters. We knew that already from Earth-based observations there was nitrogen and methane, and so we thought there would be some cool, edgy sublimation features going on. But I think it's just the fact that there was so many different landscapes that looked so different to each other, like sort of what I've shown you, this array here. So I think it's just, yes. And immediately then we realized that there was a lot more that is possible in the outer solar system than what we had thought, what we had imagined before, and that we kind of immediately thought that we're probably going to have to do a lot of reassessment as to sort of what you can do with the very limited energy sources there. And it seems you do get more bang for your buck when you sort of get all these weird volatile ices like nitrogen and methane. You can do a lot more with them with a lot less energy than you can in the inner solar system, like Saturn, for instance. Its moons are close enough in such that it's pretty much dominated by water ice. You need a lot more energy to mobilize water ice there, but yeah, the outer solar system, it seems, yes, there's a lot more weird stuff going on than we expected. So probably not one feature in particular, just the whole panorama was, yeah.
That makes sense. All right, so I think we have some questions.
Okay, I'm just going to stick this up because it'll give you a laugh, but this is Arrokoth if you were to stick it in the bay to scale.
So thanks very much for your talk. Yeah, just the incredible detail and the amount of variety of these places is just mind-blowing. I'm going to stick with a more general question that has to do with what makes a place out there have an atmosphere and hold on to it rather than it go away? And is that process different in the Kuiper belts than it is in the inner solar system?
So yes, I mean, when it was discovered back in the 80s, it was kind of a surprise that such a small object has managed to retain an atmosphere. But I think what really, I mean, it is slowly stripping away, but it's probably by the end of the solar system, there'll still be some there. But I think what really keeps it around is the constant active geology happening. So a lot of the active geology we see a lot of it's due to deposition and resublimation of atmospheric gas. So the atmosphere isn't sort of passive. It's not just sitting there waiting to be sort of stripped off by solar wind. I mean, Pluto has very active, very extreme seasons. Not just the seasons, but also its obliquity cycle. So its axial tilt can actually changes on sort of on about a 3 million year cycle. And basically, this just sets up very active sort of cycle of a deposition of volatiles for the atmosphere, sort of forming ice on the surface and then resublimating when conditions are right. So it's basically, this is kind of, I think, a main sort of process that keeps the atmosphere there, is the fact that a lot of the time it's sort of spending a lot of its time solidified out onto the surface before there are periods when it's released back into the atmosphere, and so creates a thicker atmosphere. But I think it's, yes, the fact that it's always in motion, it's always sort of interfacing with the surface volatilized geology, that is probably what maintains it, and has probably prevented it from getting stripped away, because when it's solidified onto the surface, it can't be stripped away by solar wind. So I think probably why it's managed to maintain it. Charon, we don't know if it really did have one, but Charon has probably proved much too small, only sort of a half the diameter. So if it did have one, it would have been stripped off. There was evidently no way that it could have held onto its atmosphere. I'm not sure we really know. There's probably just hypothesized whether other outer solar system, other Kuiper belt objects might have them. I think it's possible Eris might, the highest mass Kuiper belt object, but Pluto has shown us it's possible, so it's probably replicated across a bunch of the larger Kuiper belt objects.
Thank you. Really interesting talk. Thank you very much. At one point, you compared the hardness of water ice on Pluto to that of granite. Is it really harder than it forms on Earth?
Yes, I guess I don't have any hard numbers to back that up. I think I maybe use granite because it's just an example of a very hard rock, crust-forming rock on Earth. But water ice will absolutely not flow glacially at Pluto conditions like it will on Earth. It is extremely immobile and hard to mobilize. That's why I guess I mentioned the cryovolcanism that might be based on water ice. It would probably have to be mixed with some impurity. Probably ammonia is often invoked as a sort of an impurity that would reduce the melting temperature of water ice in the outer solar system and make it more amenable to mobilization. But pure water ice itself, I think I just invoked granite as a means to say this stuff isn't going to flow away anytime soon.
I would like to reiterate the spectacular amount of data you gave us today. It's amazing what we've been able to learn.
Thank you.
I am curious, do you have any idea what the density of Arrokoth is, since it formed in such a tenuous gravity well? I wouldn't expect it to be, super compact.
That's exactly correct. I don't think we have any direct observations of it, but we do think it is extremely porous, that extremely low gravity, extremely low impact speeds. There is very little in there that's going to cause the material it's made of to be very compact. And there's been some experimentations, sort of modeling done of this. One of the other New Horizons team members, Bill McKinnon, has a paper out called Snow Crash, which describes what should happen with sort of these impacts at incredibly low speeds into very porous bodies, and it's almost kind of like just basically the surface just sort of is just forced downwards. It's not really, they're sort of more like dents than true impacts really that we see in the inner solar system, where they probably wouldn't be all that explosive, there wouldn't be that much energy released. So yes, it is thought to be sort of a highly porous body. Perhaps we see some evidence of that with some of the like pit chains that I showed that might indicate surface collapse into interior voids along sort of lines of weakness between some of these accretional units.
The low energy,
I mean, probably much less than 1 gram per centimeter cubed we're dealing with here.
the low impact collision, that idea kind of passed my mind when you were talking about the potential volcano on Pluto, because it's such a large mound. It's a crater-like structure. It seems like maybe a low energy impact could do something like that too, since it's
possibly
a slushy kind of nitrogen field or whatever.
So yeah, it's interesting you mentioned that being possible being an impact crater, because one hypothesis for right mons is that maybe the kind of weird hummocky texture we see might indicate sort of individual flow fronts, but there's another idea that's come up that it may not be actual cryolavas, but it may be some sort of outgassing of like methane gas there that is then redepositing and sort of creating a somewhat accretional texture, kind of like what I showed in Pioneer Terra, but just sort of creating this sort of hummocky texture, sort of settling out across the surface. So it's a question of whether that sort of the giant sort of mountain with the giant depression, maybe is it an actual volcanic vent, or maybe it is something like an impact crater that's just been coated along with terrain around it by sort of this redepositing methane ice. Yeah, I'm not sure that it's something that's going to be definitively solved with the current data. It probably might help having things like more laboratory investigations on some of how some of these odd ice mixtures behave there, but yeah.
Thank you for the great talk and all the insights. I was wondering about more on the technical side of what kind of instructions can you send to the New Horizon? And I mean, everything being so far away, how much of it is pre-planned for the exposure of the images? Because you said for that further object, the exposure had to be higher, right? So that you can reveal the details. So how much of it is responding to what you've already taken pictures and seen, being so far, right? And how much of it is all the pre-planned? Thank you.
I mean, both of the flybys were all entirely pre-planned, all automated. I mean, we were sitting there on the morning of January the 14th, sort of seeing the progress of it happening with like NASA's eyes on the solar system. And yeah, just knowing that, yes, all of this was pre-programmed, every observation, because yes, I mean, it was like 4.5 hours return, 9 hours return trip, signal time. You can't really like change something at the last minute as it's happening. And yes, so for Pluto, it was easier because at least for Pluto, we knew exactly what its orbit was and exactly where on the surface New Horizons would be pointing for each observation. Arrokoth was rather harder because we only discovered it in 2014 and we flew by it sort of a bit more than 4 years after that. So we still weren't entirely sure of what its orbital trajectory was. We sort of could refine a little bit in the months sort of up ahead of it, but we still weren't entirely sure on the day itself whether the commands we'd fed it would result with all of it being in the frame. We thought there's a possibility we might only get a bit of it, so that was quite nerve-wracking, but we were all relieved to see when it did actually manage to get all of it in the frame. And yes, the exposure is kind of extremely tricky for Arrokoth because yeah, we had to do a careful balancing act between sort of basically just how fast it would pan and sort of the sort of length of exposure and just making sure, so basically making sure that we're getting enough photons such that we can actually sort of overcome the signal to noise ratio, but not so much that we get sort of some like blurry sort of because it had to pan quite fast, because it was traveling past this tiny object at sort of a few tens of kilometers per second, and had to pan quite fast to make sure it could sort of see all of it. We had to make sure, trade off sort of the long exposure time with sort of not panning so fast that we get blurry sort of imaging. So I think they kind of nailed it as good as they could. So yes, that's, out of all flybys, planetary encounters in the solar system, this I think was one of the toughest to plan for. There was quite a lot acting against us.
Thank you.
I have two questions. The first is, was Charon discovered at the same time as Pluto?
No, Charon was discovered in 1978 by, I think, an astronomer, James Christie, at the American Naval Observatory. Yeah, so it was discovered sort of 48 years after Pluto was.
And what's the most important unanswered question about Pluto?
Well, I'd kind of like to see what's in the part that were hidden to us in the southern latitudes, and also I'd kind of like to sort of get some better view of the side that we didn't see up close. I mean, given how many surprises it's thrown at us with sort of the part we did see, I think wouldn't surprise me if there's a few other tricks up its sleeve. But yeah, I think. So yeah, I would like to see more of it, but as for, I guess, an actual unanswered question, I think for me it would be to what degree has volcanism shaped its surface? In a question before, sort of was about right mons, what we think might be a volcano. I'm curious to see, I'm curious to find out if volcanism has sort of been a major element in shaping its surface. We've sort of had a little tease of what might be a volcano now, but I'd sort of want to see more evidence so we can really say whether it has volcanism or not on its surface. And for that, we need to see all of it.
Thank you.
Okay.
Firstly, thank you. That was very fascinating. I'm serious. How can we tell the difference between ridges or valleys that are formed when two planetesimals collide and craters that are formed when an object just hits and leaves a crater?
So this is with respect to Arrokoth?
Yes.
So again, the first part of the question, how do you, what was
You said, sorry, you said there was, I don't remember which planet it was.
Basically are you talking about sort of what the origin of the pits are?
Yes, you said
Yes.
that one side was made of planetesimals crashing into each other, but then the other one, the planetesimal didn't stick around, basically.
Well, no, I think so. Yes, I guess we've got a couple of googly eyes here, but so I think both lobes form the same way. It's just that, so I think the smaller lobe originally did have this texture that we see on the larger lobe, these separate accretional units. It's just that a sky crater impacting, well, it was probably a very low energy impact. It was still enough probably to sort of eliminate sort of some of these what appear to be sort of boundaries, but separate accretional units that we see on the larger lobe. So actually, one of the more recent papers on Arrokoth geology, I did a little geologic map that where sort of I indicated what I thought were the locations of the accretional units on the large lobe, and I indicated just sort of a bit hand wavy, but what I thought might be a couple of possible accretional units that are surviving on the limb of the small lobe, but it's really touch and go as to whether they are that, and they exist on the part of the small lobe that's far away from the crater. So yes. So yes, I think they both form the same way. It's just the small lobe is arguably less primitive because that primitive texture of the accretional units was probably wiped out by the crater. It's possible if we saw the other side of the small lobe, they might still be kind of manifesting there, but Yeah, we
Yeah.
didn't see the other side, so
Sorry,
who
stupid
knows?
question. Thank you, though.
Let's thank Dr. Whiting.
Thank you.